Let's see this beautiful curve. So let x-axis pointing into the paper. By the right-hand rule, still remember that when we construct the 3D space coordinate system, we use the right-hand rule. So x is pointing into the paper, y is pointing upward. Then the z-axis will be pointing rightward, right? Now, at least we know that, okay, it is a non-uniform bar. That means the cross-sectional area of this bar is no longer a constant. It will become a function of z. So A is AZ. Under external load P, for every position of this beam, the axial strain will be different. So still remember that in case we have the load P, that means everywhere in this beam will exert the load P, right? For any place, everywhere in the beam, you will have the direct force P acting on this variable area AZ. We know that epsilon equals to sigma divided by E, which equals to P divided by AE. But now, AZ is a variable instead of constant. So just now, in the uniform bar case, we know that the strain is constant everywhere. But now, A is a function of Z. So as a result, the axial strain, epsilon, at every place of this bar are varying. They are changing along the z-axis. Let's give this uniform bar an assumption, which is very often. That is, we set E to be constant everywhere. Then P, E are constant. Then we just consider the change of the area. At some position Z, the stress at this position will become P divided by A of Z. Then you can find the local strain. Epsilon Z equals to sigma Z divided by E. Then you make the substitution. We know that from previous case that delta equals to epsilon L, right? But we consider a slice, a thin sheet of material with the variable sectional area, which has the thickness dz, very small thickness. Then for this differential segment, the deformation will become delta equal to epsilon times dz. dz is the differential length of this slice. So for this slice, it is very thin, okay? So we assume on this very thin slice, the epsilon, the strain, will be the same over this very small slice. And then we just use this relationship to find d delta equals to epsilon of z times dz. Finally, we combine all those relationships, then we can find the differential change of length, which is P times dz divided by EA of z. And finally, you take the integral. Then you will get this result. A remark is that in the textbook, they use X instead of Z because in this course we only consider the 1D loading. What does that mean? That means maybe your loading is like this, but it is 1D. In the reality, not only 1D, we still have the loading, which is about x-axis, which is pointing to the x-axis, but you cannot see it here. So in this course, we only consider 1D loading, but I still recommend you to use Z, because in advanced solid mechanics course, we will use Z instead of X, because X is often used to calculate the sectional properties. I will introduce that to you later. However, one thing you have to know is that in the lab or in the problems we are going to solve in this course, we will often see a term called strain gauge. What is strain gauge? Strain gauge is a sensor to measure the local strain of a piece of material. So for example, if you place a strain gauge here and you place a strain gauge here, so there are two sensors. Those two sensors are detecting the local strain on that particular point, and they will give you a reading. So which one do you think the reading will be bigger? The answer is this one will become bigger. This one is bigger. Recall the formula of the strain. The strain is given by the local stress divided by the Young's modulus, where the local stress is given by the applied load divided by the local cross-sectional area. So of course here the cross-sectional area is much more smaller. So the local strain here will be very large in comparison to that of here.